I want you to picture something like incredibly mundane. Something you probably did this morning without even really registering it.
Right, like brushing your teeth.
Exactly. Or, maybe you flicked a light switch on your wall. Or maybe you turned the dial on a gas stove to boil water for your coffee. Or stood at a gas station filling your car with petrol on the way to work.
Yeah, those actions just feel like the absolute baseline of our modern routine. We perform them entirely on autopilot.
We do. Because, there's nothing magical about a plastic switch or a metal nozzle.
No, not at all.
But if you look a little closer at what is actually happening in that split second and doing those boring everyday actions, you are commanding something genuinely astonishing.
You really are.
You're reaching back through deep time across this geological span that is so vast the human mind kind of struggles to even hold it. And you are releasing energy that arrived from the sun hundreds of millions of years ago.
Yeah, when you strip away the machinery and the infrastructure, fossil fuels, so, the coal, the oil, the natural gas running the modern world, they are a direct physical link to the ancient Earth.
It's wild to think about.
It is. They are not just rocks or fluids. They are a profoundly strange geological anomaly.
And that anomaly is our mission for this deep dive. Because we base our entire civilization on these materials, yet we rarely stop to ask the most obvious questions, right?
Right, like what physically are they?
Exactly.
Yeah.
Where do they come from? And why are they miraculously useful while also being, the defining crisis of our time?
Yeah, that's the big one.
So we're going to explore this origin story, which is honestly one of the greatest narratives of Earth's history. Because understanding how these fuels were made explains pretty much everything about our complicated relationship with energy today.
So to understand how a burst of ancient sunlight ends up propelling a 2-ton car down the highway, we have to start at the very beginning of the supply chain.
Okay, take us there.
We have to look at how solar energy actually gets trapped in the physical world. It sounds a bit like poetry to call fossil fuels stored sunlight, but it is an absolute literal truth.
See, that's the part that tricks me up. Sunlight is just, transient radiation, right? It hits the ground, it warms things up, and then it just dissipates. How does light become a tangible, highly combustible rock?
It begins with photosynthesis.
Ah, okay, back to biology class.
Right, but we often think of photosynthesis simply as how plants feed themselves. It's better understood as nature's original solar-powered manufacturing process.
Well, I like that.
Living organisms, whether they are towering ferns on land or, microscopic algae floating in the ocean, they have the ability to capture the energy of incoming solar photons.
So they act like tiny biological solar panels.
They do. But unlike a solar panel on your roof that just generates a current, these organisms use that captured solar energy to perform heavy chemical lifting.
What do you mean by chemical lifting?
Well, they pull carbon dioxide gas directly out of the air or the water around them. They strip the carbon out of it, and they use that carbon to build their physical bodies, their stems, their leaves, roots, cell walls.
So every leaf on a tree, every blade of grass on your lawn, and every patch of ocean algae is essentially this physical package of captured solar energy and atmospheric carbon.
Exactly. That solar energy is physically locked into the tight chemical bonds holding the plant's tissue together. The organism built itself using the sun's power.
Right.
But in the normal course of nature, that storage is incredibly temporary.
Because nature runs a pretty ruthless recycling program, doesn't it?
It absolutely does.
Like, think about a compost bin in your backyard. When a plant dies or an animal that ate that plant dies, it doesn't just sit there intact forever.
No, it becomes a buffet.
Right. Scavengers eat it, insects break it down, and then microscopic bacteria and fungi just rot it away.
And that decay process is really just photosynthesis running in reverse.
Yeah.
The bacteria are breaking those chemical bonds to feed themselves.
Okay, so the energy gets released.
Yeah. As they do that, all that stored solar energy is released back into the environment as ambient heat. And the carbon that the plant originally pulled from the air is released right back into the atmosphere as gas.
So the compost bin eventually empties out, the carbon goes back into the air, the next generation of plants uses it again, and nothing piles up. The ledger is perfectly balanced.
Exactly balanced. And the defining plot twist of our modern world is that fossil fuels only exist because of incredibly rare freak occurrences where that natural recycling program was just abruptly interrupted.
The compost bin gets slammed shut and sealed.
Permanently. Instead of being eaten or rotting away, massive quantities of this dead living matter were buried intact. The ordinary, everyday process of decay simply stopped.
But that seems totally counterintuitive. I mean, if everything on Earth, from fungi to bacteria, has evolved to exploit dead organic matter for food, what could possibly happen to interrupt that?
It's a great question.
Like, how does millions of tons of biological material avoid rotting?
It really comes down to geography. Specifically, it's a tale of two very different ancient graveyards. The environment dictated the interruption.
Okay.
Let's look at the first graveyard, the one that gave us coal, because it paints an incredibly vivid picture of the ancient Earth.
Set the scene for me. How far back are we actually going here?
We are winding the clock back over 300 million years.
Oh, wow. So way, way back.
Yeah, to a period geologists appropriately called the Carboniferous. This is long before the first dinosaurs walked the Earth.
Okay, no T-Rexes yet.
None. The continents were arranged completely differently, and vast stretches of the landmass were covered in sweltering, steamy swamp forests.
I am picturing, like, giant ferns, dense humidity, just a very alien-looking jungle.
Spot on. Immense trees, some of them 100 feet tall, towering over these waterlogged swamps. And when those massive plants died, they naturally just toppled over.
Right.
But they didn't crash onto dry, aerated soil where fungi could quickly devour them. They fell directly into the stagnant swamp water.
And stagnant water is the key here.
Yeah.
Right. Because we have swamps today, but we aren't exactly watching new coal beds form in the Everglades in real time.
Exactly. What was different about these waters was that they were profoundly oxygen poor. Biologists call it anaerobic.
Okay, so no oxygen.
Right. Because the water was deep, still, and choked with debris, oxygen from the air couldn't mix into it. And the bacteria and fungi that normally break down dead wood, well, they desperately need oxygen to survive and do their job.
Oh, so the decomposers literally suffocate. They can't survive in the swamp water to eat the fallen trees.
That's exactly it. The trees fall in and they just sit there perfectly preserved in the muck. Now imagine that happening layer upon layer, year after year, for millions of years.
That's just a staggering amount of unrotted, dead swamp forest piling up.
It is. It forms this thick, spongy, waterlogged material known as peat.
So a peat bog is basically a massive, soggy layer cake of ancient solar energy and carbon that nature just failed to recycle.
Exactly. But peat is not coal.
Right.
It is just the raw ingredient. To turn that spongy plant matter into the hard, black rock we burn today, you need deep time and extreme geological violence.
Hey, geological violence. I like the sound of that.
Well, over millions of years, the Earth's climate shifted. Sea levels rose and fell, and those ancient peat swamps were eventually buried under mounting layers of sand, mud, and sediment.
So the immense weight of the Earth's crust starts pressing down.
Millions of tons of pressure. As tectonic plates shifted, this peat was dragged deeper and deeper underground. The mounting pressure physically squeezed the water and impurities out of the spongy matter.
Okay.
And at the same time, the deep geothermal heat of the Earth began to cook it.
So it's essentially being pressure cooked in a sealed geological oven.
That is the perfect analogy. That combination of immense weight and deep Earth heat fundamentally rearranged the molecules. It concentrated the carbon, transforming loose, wet plant matter into dense, energy-rich seams of coal.
So literally every lump of coal is quite literally the compressed, cooked remains of a 300-million-year-old forest.
Every single lump.
That is incredible. Okay, so that covers the swamps and the coal.
Yeah.
But you mentioned a second graveyard.
I did, yeah.
When we look at oil and natural gas, we're dealing with liquids and gases, not solid rocks. So where does that story take place?
For that, we have to leave the land entirely and move to the ancient oceans. The mechanism of interrupted recycling is identical, but the organisms involved are completely different.
Okay, let me stop you right there, because I think a huge portion of the public, myself included, grew up with a very specific, almost cartoonish image in our heads.
The dinosaurs.
Yes, we see a dinosaur logo on a gas station sign. Are you telling me that when I am pumping unleaded petrol into my car, I am not actually pumping liquefied T-Rex bones?
I am so sorry to burst the bubble, but the dinosaurs are entirely innocent in the story of oil.
My whole childhood is a lie.
It is a very persistent myth, but a fossilized dinosaur bone is just rock. The real source of oil is vastly more abundant and much, much smaller.
So if it's not a brachiosaurus, what is actually fueling my car?
Picture the surface of the ancient sunlit oceans. They were absolutely teeming with countless microscopic organisms, phytoplankton and tiny algae floating near the surface, conducting their own microscopic photosynthesis.
turning solar energy into tiny carbon-based
Oh,
bodies.
exactly. Trillions upon trillions of them.
Just floating solar panels by the trillions.
Yeah, and just like the swamp trees, their lifespans were pretty short. When they died, they drifted down through the water column like a continuous microscopic snowstorm.
Okay, I can picture that.
Eventually, they settled on the ocean floor.
And I'm guessing the bottom of these ancient oceans suffered from the same lack of oxygen as the swamps.
You've got it. In certain specific marine basins, the deep water was entirely stagnant and completely devoid of oxygen.
So the scavengers and bacteria that would normally feast on that rain of dead plankton couldn't survive.
They couldn't survive in those deep anoxic zones, so the microscopic bodies just piled up, forming this thick, dark, organic ooze on the seafloor.
It's the exact same plot twist. The recycling gets interrupted again. But how does ocean ooze become liquid crude oil instead of a rock like coal?
That comes down to the starting material and the specific temperature of the geological oven.
Okay, explain that.
Well, ocean plankton have a different chemical makeup than woody land plants. They are much richer in lipids or fats. So as this marine ooze was buried under millions of years of silt and rock, it was pushed deeper into the earth.
Hitting that pressure cooker again.
But for oil, the temperature has to be incredibly precise. Geologists actually call it the oil window.
The oil window.
Yeah, if the ooze is buried at a depth where the temperature is between roughly 60 and 120 degrees Celsius, it cooks into liquid crude oil.
Oh, like baking a cake. You need the exact right temperature or it ruins it.
Precisely. If the tectonic forces push it even deeper, where the temperatures are significantly hotter, those molecules break down further and cook into gaseous natural gas.
Wow. But wait, the Earth's crust is highly volatile, right? Tectonic plates smash together, earthquakes happen, volcanoes erupt.
Very volatile.
So how does a pressurized, volatile liquid like oil just sit underground for 100 million years without leaking out to the surface?
Well, because oil and gas are fluids, they don't actually stay in the deep source rock where they were cooked.
Oh, they don't.
No, they are lighter than the water trapped in the rocks around them, so they slowly seep upward. They migrate through layers of porous rock things like sandstones or limestones that act like hard underground sponges.
So they're constantly trying to bubble up to the surface.
They migrate upward until they hit an absolute roadblock. In certain geological formations, layers of impermeable rock, like dense shale or solid salt, were folded into dome-like shapes by tectonic pressure.
Okay, and fluids just simply cannot pass through these dense layers.
Exactly. The dome acts as a permanent, impenetrable lid.
I see.
The migrating oil and gas hit the underside of that dome and became trapped within the microscopic pores of the sponge-like rock beneath it. They just pooled there.
Building up immense pressure over millions of years.
Right, creating the massive underground reservoirs that we drill into today.
Okay, so synthesizing this for a second. Coal is the buried, cooked graveyard of ancient swamp forests, and oil and gas are the buried, cooked graveyards of ancient ocean plankton.
That's it.
They were just different chapters of the exact same story, nature's recycling program getting interrupted, allowing biological solar storage to be locked away over deep time.
That is a perfect encapsulation.
All right, so that explains what they are and where they come from. But it brings us to, I think, the most practical question of all. Why do they matter so much?
In what sense?
Well, why does a relatively tiny tank of this ancient ocean liquid contain enough raw power to propel a heavy steel vehicle for hundreds of kilometers at 80 miles an hour? I mean, a tank of wood chips certainly couldn't do that.
No, it definitely couldn't. The sheer punch these fuels pack really comes down to two factors: concentration and chemistry. Let's look at concentration first.
Yeah.
Think about what it takes to grow a single oak tree or a dense patch of algae over a summer. That represents a specific limited amount of captured sunlight.
Right, it's just whatever hit those leaves during those few months.
But when you burn fossil fuels, you are not burning a single season of growth. Because these graveyards piled up for millions of years and were then violently compressed by the Earth, a single lump of coal or a single gallon of gasoline represents the accumulated solar capture of countless millions of organisms.
All squeezed into an incredibly dense package.
Exactly.
It is essentially a planetary battery.
Oh, I love that.
Right. Like the Earth spent hundreds of millions of years painstakingly trickle-charging this massive storage system using tiny daily drops of sunlight.
Yes.
And humanity just figured out how to plug a wire into it and discharge that entire geological epoch in a single explosive moment.
Planetary battery captures the sheer scale perfectly. The mismatch in time is staggering. But the second reason for their power is the specific chemistry forged in that underground oven. It's about the molecular bonds.
Okay, break that down for us. Because I know a chemical bond is just the force holding atoms together, but why does that equal so much energy?
Well, fossil fuels are hydrocarbons, meaning they are primarily made of carbon and hydrogen atoms heavily interlinked.
Right.
Think of those chemical bonds like highly compressed physical springs holding the atoms together in a really stable grid.
So they are sitting there perfectly stable, but loaded with potential energy.
Exactly. And they need a catalyst to release it. In an engine or a power plant, we introduce oxygen and a spark of heat that's the activation energy.
Which triggers combustion.
Right. The heat breaks those stable carbon and hydrogen bonds apart.
The springs snap.
They snap violently. The carbon and hydrogen atoms rapidly combine with the oxygen from the air to form new molecules, carbon dioxide and water.
Right, I follow you.
But here's the critical part. These new molecules require much less energy to hold together than the original hydrocarbon did.
So the atoms settle into a lower energy, more relaxed state.
Yes.
But wait, energy can't just disappear. Where does that excess energy go?
It is violently expelled outward as searing heat and expanding gases. That explosive outward force is what pushes the piston down in your car engine, or spins the massive turbines in a power plant to generate electricity.
So you are tapping into a hyper-concentrated material loaded with millions of years of coiled molecular springs, snapping them with oxygen to harness the explosive release.
That's exactly it. And that unprecedented energy density entirely rewrote human history.
It really did.
Before fossil fuels, we were limited by the real-time solar budget. We relied on the wind to push sails, the muscle power of animals fed by recent crops, or burning recently felled wood.
Which works. But wood is bulky.
Yeah.
You have to burn a massive volume of it to generate the heat needed to, say, forge steel on an industrial scale.
Right, and fossil fuels shattered that bottleneck. Suddenly, humanity had access to something unbelievably dense, highly combustible, and incredibly portable.
You just put liquid energy in a barrel and ship it across the globe.
Exactly. It powered the steam engines of the Industrial Revolution, the combustion engines of global logistics, and the massive electrical grids that run the modern world.
It's essentially the foundation of our entire civilization.
It is.
But, I mean, that brings us to the looming shadow over this whole story. If fossil fuels are this spectacular, energy-dense planetary battery that gifted us modern life, why is utilizing them the defining existential crisis of our era?
It's a heavy question, but it's because the phenomenal energy we just explored and the climate crisis we are currently terrified of are inextricably locked inside the exact same molecule.
So they're two sides in the same coin.
They are. Let's look at the basic math of deep time. We established at the very beginning what fossil fuels physically are.
Right, they are carbon. Carbon that ancient plants and plankton physically pulled out of the Earth's atmosphere.
Yes. The living biosphere scrubbed that carbon from the sky, and geology buried it in a sealed vault deep underground.
It was taken completely out of the active carbon cycle for hundreds of millions of years.
Exactly. The Earth's climate stabilized based on an atmosphere that no longer contained that massive volume of carbon.
So nature essentially archived all that excess carbon in the planet's basement.
And now, look at the sheer velocity of modern industry. We are locating those geological vaults, drilling into them, and unearthing that carbon.
Oh, wow.
We are taking a stockpile that required hundreds of millions of years for the Earth to slowly sequester, and we are violently burning it, releasing all of it back into the modern atmosphere in the span of roughly 2 centuries.
The scale of that imbalance is terrifying. We are basically running geological time and fast forward.
We really are. We are reversing a 100-million-year burial process in a few generations.
So when we break those hydrocarbon bonds for energy, the carbon combines with oxygen and is expelled from the exhaust pipe or the smokestack as carbon dioxide.
And carbon dioxide is a potent greenhouse gas.
Right, we hear the term greenhouse gas constantly.
Yeah.
But what is the actual physical mechanism? Why does a specific invisible gas warm the planet?
It has to do with how the gas molecules interact with different types of light. The sun's energy hits the Earth as shortwave radiation, mostly visible light. Carbon dioxide is transparent to visible light, so the solar energy passes right through the atmosphere and warms the surface of the Earth.
The sunlight gets in just fine.
But the warm Earth radiates that heat back outward towards space as long-wave infrared radiation, and carbon dioxide molecules are specifically structured in a way that absorbs infrared radiation.
Oh, I see.
When the heat tries to escape, it hits the CO2, causing the molecule to vibrate and scatter the heat back down toward the
But
surface.
it acts like a one-way mirror,
Yeah.
or like a thermal blanket. The heat gets in, but it can't easily get back out.
Exactly. The more ancient carbon we dig up and pump into the air, the thicker that invisible thermal blanket becomes, trapping more heat and destabilizing the global climate.
Which brings us to the core revelation here. The climate crisis isn't a side effect. It's not like sulfur or smog, some impurity in the coal that we can just invent a better filter for or scrub away in a laboratory.
It is the main event. This is the tragic paradox of fossil fuels. You physically cannot access the buried energy without also releasing the buried carbon.
Because they are exactly the same thing. To snap the molecular spring and get the heat, you have to break the bond. And breaking the bond means the carbon is free to bond with oxygen and enter the atmosphere.
The very feature that makes coal and oil magnificent energy sources, the incredibly dense accumulation of carbon stored over deep time, is precisely the mechanism that warms the planet when combusted.
You cannot separate the power from the pollution.
You can't. We are trying to unpick a molecular knot that nature tied over millions of years.
That completely reframes how I view our energy infrastructure. We aren't just burning fuel, we are burning a piece of ancient history that comes with an unavoidable built-in consequence.
Understanding that single biological and geological connection is the skeleton key to understanding our current global predicament.
Right.
It explains exactly why fossil fuels accelerated human progress so rapidly, and it explains why transitioning away from them is the most complex engineering challenge our species has ever faced.
Let's take a breath and recap this immense journey, because we have covered the entire lifespan of the planet's carbon cycle today.
It's a lot to take in.
It really is. We started by realizing that fossil fuels are physically ancient sunlight. The sun's radiation was captured by life, vast swamp forests on land, and microscopic plankton floating in ancient seas.
And that biology died, but the normal recycling process of rotting was interrupted by oxygen-starved, stagnant waters. The scavengers suffocated, and the carbon was buried intact.
Then, millions of years of heat and crushing tectonic pressure cooked those graveyards, concentrating them into the incredibly dense coal, oil, and natural gas reserves we extract today.
That deep time incubation forged molecular bonds with an energy density nothing else could rival. It gave us the cheap, portable planetary batteries that powered the Industrial Revolution.
But they came with a catch, built into the fundamental chemistry. To use the buried ancient energy, we have to unbury the ancient carbon. We're releasing hundreds of millions of years of stored carbon dioxide back into our modern atmosphere in just a few centuries, thickening the thermal blanket and trapping heat.
The energy we rely on and the climate problem we fear are physically identical. You truly cannot have one without the other.
So to bring it all the way back to the beginning, the next time you switch on a gas stove to make dinner or start your car's engine, take just a single second to appreciate the sheer scale of what you are doing.
Yeah, it's quite profound.
You are not just pushing a plastic button or turning a metal key. You are commanding the explosive power of millions of years of ancient sunshine, marshland, and deep ocean life. It is an absolute miracle of nature that built our modern reality, but it is a miracle we must now urgently figure out how to outgrow.
And as we navigate that difficult transition, I want to leave you with one final thought to mull over.
Okay, what is it?
We just spent this entire deep dive exploring how fossil fuels are fundamentally a mistake in nature's recycling program.
Right.
Organic matter that accidentally got buried instead of rotting away, eventually becoming our greatest fuel source and our most existential threat.
The interrupted compost bin that changed the world.
Look around at our world today. What modern synthetic materials are we mass producing and burying in massive landfills right now? Materials like plastics and synthetic chemicals that deliberately interrupt nature's normal recycling program because they cannot rot.
Oh.
What are we sequestering today that might become strange geological treasures or perhaps absolute environmental nightmares for whoever might be digging through our planet's crust millions of years in the future?
Now that is a thought that is going to linger.
Yeah.
Thank you for joining us on this deep dive.